Good morning, and thank you for your participation. My name is David Lauer, and I am Vice President of Marketing and Business Development at Enviromix. This morning, I will be introducing BioMix DC Enhanced Anaerobic Mixing System, along with my colleague, Sarah Elger, Director of Product Innovation and Strategy. At the end of the presentation, we will be taking a few questions from the audience. Please use the Q&A function at the bottom of the screen if you want to send us questions. BioMix DC Enhanced Anaerobic Mixing System maximizes volatile fatty acid formation and utilization by the biomass. BioMix DC enhances biological phosphorus removal for consistently low effluent phosphorus. BioMix DC provides energy savings of 90% or greater, and BioMix DC minimizes chemical addition and sludge production. Today's agenda for the presentation will be an introduction to enhanced biological phosphorus removal and anaerobic fermentation, introduction of Enviromix's BioMix DC Enhanced Anaerobic Mixing System. We will present details of the Warren, Michigan case study with results of BioMix DC performance. And finally, we'll provide a summary and answer a few audience questions. Before we move on, we'd like to ask the audience a question. Do you currently have phosphorus regulations? We'll give you a couple moments to respond. Okay, let's review the results of the survey. All right. Well, from the results, it looks like the majority of those that responded already have a phosphorus regulation or expecting them in the future. That's perfect because this presentation should be of great interest to you. Now we'd like to provide a brief introduction of enhanced biological phosphorus removal and anaerobic fermentation. Enhanced biological phosphorus removal, or EBPR, relies on the selection and proliferation of a specialized microbial population capable of taking up phosphorus in greater amounts than their normal biological growth requirements. EBPR uses sequential anaerobic and aerobic environments to provide conditions that encourage the growth of these specialized phosphorus accumulating organisms, or PAOs. Uptake of phosphorus occurs under aerobic conditions, but PAOs must first be conditioned by exposure to volatile fatty acids, or VFAs, under anaerobic conditions. PAOs store excess phosphorus in their cell mass, and phosphorus is removed with the waste sludge. Under anaerobic conditions, PAOs use polyphosphate and glycogen stored in their cells as energy sources to enable them to uptake VFA. VFAs are converted to PHA and stored in the cells of PAOs. As they take up VFA, the PAOs release orthophosphate into the mixed liquor. PAOs' ability to uptake food in the form of VFAs give them a competitive advantage over other bacteria. Under aerobic conditions, PAOs use PHA as a source of carbon and energy for metabolism and cell growth. PAOs restore their supplies of glycogen and polyphosphate in the aerobic zone. To replenish their stored polyphosphate, PAOs will take up excess phosphate from the mixed liquor. Uptake of phosphorus is dictated by the amount of VFA stored by PAOs and the energy and phosphorus released in the anaerobic zone. Anaerobic fermentation is a common way to boost VFA formation. EBPR success is primarily determined by influent wastewater quality and the amount of VFA present in proportion to the amount of phosphorus to be removed. VFAs are created through the process of hydrolysis and fermentation, as shown on the image to the right. Complex organic matter, such as carbohydrates, proteins, and fats, are broken down by enzymes to create soluble organics such as sugars and acids. Facultative bacteria then convert soluble organics to VFAs. To encourage fermentation in the anaerobic zone, it is important to maintain optimal anaerobic conditions by allowing mixed liquor to settle, to accumulate, and increased solids retention time in the zone. The most critical factors of EBPR are the integrity of the anaerobic zone and the availability of VFAs. Therefore, the keys to EBPR are an anaerobic zone with strict anaerobic environment, which means negligible free oxygen or bound oxygen, no dissolved oxygen or nitrate. An anaerobic environment with low oxidation reduction potential, less than negative 150 millivolts, an anaerobic fermentation layer capable of generating VFAs, the optimal mixing regime to produce VFA and transport VFA to the PAOs, surplus VFA production leading to the proliferation of PAOs, whereby PAOs are never VFA limited, with the end goal of low levels of effluent soluble phosphate. Sarah will circle back to these critical factors when she presents the test results from the Warren case study. In keeping with those keys to EBPR, Enviromix introduces BioMix DC, Enhanced Anaerobic Mixing System. BioMix DC enhances the anaerobic fermentation process by combining a long deep cycle with optimized mixing cycle. In the deep cycle, long periods without mixing allow solids to accumulate, creating a fermentation layer near the bottom of the anaerobic zone, producing VFAs, which are transported to the PAOs through intermittent pulses of mixing without disrupting the fermentation layer. Following the deep cycle, compressed gas mixing quickly resuspends the solids to homogenize the substrate and microorganisms. In the deep cycle of BioMix DC, long periods without complete mixing causes the aerobic zone to stratify, with lower concentration of biomix near the surface and causing solids to accumulate at the bottom of the zone. The accumulating solids at the bottom of the zone create a sludge blanket or fermentation layer. This fermentation layer drives down ORP and creates an environment of increased VFA production. The accumulating solids of the fermentation layer increase anaerobic solids retention time, generating surplus VFA, thereby enhancing biological phosphorus removal. To further enhance biological phosphorus removal and create a stable process, the creation of excess or surplus VFA is important. It is also important that the VFAs are accessible to the PAOs throughout the anaerobic zone, not only in the fermentation layer. BioMix DC provides intermittent pulses of mixing during the deep cycle to transport the VFAs to the PAOs in the bulk liquid without disrupting the fermentation layer. No other process or mixing technology can do this. The result is better biological phosphorus removal and lower soluble phosphorus. Resuspending solids or destratifying the anaerobic zone is important to homogenize the substrate and microorganisms. Rapid resuspension destratifies the selector within minutes. Nozzles near the floor of the tank release short duration bursts of compressed air. Large compressed gas volumes expand upward and outward. Expanding bubbles provide mixing with controlled turbulence, fluid displacement, and circulatory currents. BioMix DC leverages Enviromix's core mixing technology, BioMix, which has been successfully applied in biological selector applications for over a decade. BioMix utilizes 40 to 60% less energy than mechanical mixing technologies. The bottom-up mixing regime provides uniform distribution of mixing energy at a very efficient 1/10 of a horsepower per 1,000 cubic feet of anaerobic selector volume. The control system allows for adjustment of the mixing regime and intensity based on process parameters. All in-tank components are non-clog and maintenance-free. BioMix utilizes a central compressor system, typically duty and standby configuration, to produce the necessary air volume to meet the mixing air demand. This substantially reduces the amount of mechanical equipment to be maintained versus traditional vertical entry or submersible mixers, which require a minimum of one mixer for every mixed tank. Depending on the application, the compressor system may be in a building, inside a heated and ventilated enclosure, or if ambient conditions permit, outdoors under canopy. In most applications, compressor output ramps up and down by loading, unloading, or varying speed, which in turn modulates power draw to maintain system pressure. compressor charges a receiver tank for air storage, which buffers system demand to maintain a relatively constant system-wide pressure. Depending on the application, a single centralized receiver tank may be provided, or multiple smaller receiver tanks distributed near the mix tanks. The receiver tank supplies air to the valve module, which controls the firing parameters of pressure, frequency of discrete mixing, duration of air release, and header firing sequence. Depending on the application, a single valve module may control air distribution for all of the mixed tanks, or multiple valve modules may be provided if the system is larger. And lastly, a master control panel may be provided to integrate control of multiple valve modules. Biomix utilizes patented engineered nozzles near the floor of the tank to generate large fluid displacing bubbles produced by short duration bursts of compressed air that expand upward and outward without measurable oxygen transfer due to the characteristics of the large bubbles. The mixing regime of Biomix provides bottom-up uniform mixing in any basin configuration, geometry, or floor slope. Biomix's unique operation of firing individual nozzle headers in sequence allows for nozzles to be located at different depths to follow the slope of the tank, including hopper or cone bottoms, eliminating dead zones, and maximizing tank volume utilization. Before turning the presentation over to Sarah, I'd like to ask the audience a question. How strong of a correlation do you think there is between accessibility to excess VFA and consistent BioP performance? We'll give you a couple moments to respond. Let's review the results of the survey. Very interesting. From the results, it looks like the majority of those overwhelmingly believe there is a strong correlation between accessibility to excess VFA and consistent BioP performance. Now let's see if the performance results Sarah is about to present from the Warren case confirm that opinion.
Thanks, Dave. I would like to proceed forward now in presenting the results of our testing. There we go. Sorry about that. I'd like to proceed forward now in presenting the results of our testing at the Water Reclamation Facility in Warren, Michigan. Before I start, I just want to publicly thank the plant operations and lab staff for all of their support during this testing. Not only did they allow us to come to site and use their lab to analyze dozens of samples, but they also assisted in sample collection and analysis on days when we weren't able to be on site. So thank you to Joe, Bernard, Andrew, Bob, Brian, and the rest of the staff, along with our local rep, Jay. Enviromix first worked with the Warren facility back in 2014 as a part of the Energy Savings Performance Contract that upgraded the plant from a conventional system to an anaerobic oxic or AO process. The anaerobic zones were added to facilitate biological phosphorus removal and reduce ferric chloride consumption. With the addition of Biomix compressed gas mixing to the anaerobic zone, the plant realized more than $150,000 in savings per year, including both energy and chemical savings. After the upgrade in 2014, the facility experienced an improvement in biological phosphorus removal. However, performance was not consistent enough to eliminate the need for chemical addition. The lack of consistent performance was attributed to the low influent BOD to P ratio, which was further reduced by the high levels of phosphorus in the filtrate recycle stream from their solids dewatering process. Warren often operates well below the industry recognized optimal BOD to P ratio of 25:1, which prompted the staff to consider alternatives to further improve BioP removal and consistency. Enter Biomix DC. On April 7th of this year, the Biomix DC system was turned on in Train 2 in both zones 1 and 2, as shown with the orange arrows. Train 1 was used as a control train for comparing the Biomix DC operation to the existing complete mix anaerobic selector. The goal of the testing was to prove that we could deliver on the plant's request to have more consistently low effluent phosphorus. Our hypothesis on how we could achieve this low stable effluent P was that we could ensure a deep anaerobic state in the fermentation layer to generate VFAs and transport them to the bulk liquid for PAOs to utilize for consistent biological phosphorus removal. Some of the test methods that were used included a handheld TSS meter, a sludge judge, a Hach DR6000 spectrophotometer for measurement of VFA, along with ortho and total P, and a DNA analysis. The results from each of these test methods will be discussed in greater detail as we continue. If you recall from Dave's discussion about the most critical factors for strengthening EBPR, the first requirement was having an anaerobic zone with low ORP. Prior to beginning the Biomix DC testing, we tracked ORP in Train 2, Zone 1 at mid-depth, about 3/4 of the way down the length of the tank. During this time frame, the anaerobic tank was completely mixed 24/7 with our Biomix compressed gas mixing system. As you can see, the ORP readings was very stable and averaged around -470 millivolt. ORP readings remained at this level throughout the duration of our testing during both the mixing cycle and the deep cycle. We did not measure any substantial difference in the ORP readings in the bulk liquid compared to the fermentation layer, despite the fact that we may have expected that. This could be attributed to the already very low readings at this facility. So with that, we're going to check the box that Biomix DC provides low ORP conditions to promote EBPR. Next, we will investigate the development of a fermentation layer. When mixing is suspended and solids are allowed to accumulate, it is expected that a sludge blanket will form at the bottom of the tank. To confirm this, we used both a sludge judge and a handheld TSS meter and took measurements during the deep cycle. The sludge judge shows a solids profile from the entire depth of the tank. In the top photo, you can see that in the middle of the sludge judge, light flocculated sludge is observed, typical of mixed liquor. In the bottom photo, you can see that the bottom 1 to 3 feet of the tank contained a darker, thicker sludge representing the fermentation layer. A handheld TSS meter was used to confirm the visual results. The TSS in the bulk liquid, or the majority of the tank, measured between 3,300 and 3,700 milligrams per liter. Immediately below this bulk liquid was a small layer of sludge between 6 and 12 inches with a concentration around 8,000 milligrams per liter. Below that, the fermentation layer measured greater than 1% solids, which was the limit of the handheld meter we had. These results confirm the formation of a fermentation layer in the anaerobic zone. Next, we will examine VFA generation. To determine if VFAs were being generated, samples were collected from both the fermentation layer and the bulk liquid during the deep cycle mode of operation, just prior to the start of a mixing cycle. Samples collected from the fermentation layer are shown in dark brown on the chart, whereas samples from the bulk liquid are shown in light brown, the lower values. The colors correspond to the image on the right. Results over a 10-day sample window showed substantially higher VFA readings in the fermentation blanket compared to the bulk liquid. In fact, the samples collected in the bulk liquid were all under range for the test kits that were used, which was all less than 20 milligrams per liter, whereas the samples in the fermentation layer were all in excess of 200 milligrams per liter. The presence of such high VFA concentrations in the fermentation layer indicate an abundance or excess of VFAs. The excess VFAs indicate a healthy anaerobic environment ripe for the first step in biological phosphorus removal. The abundance of VFAs indicates that the PAOs that are present in the fermentation layer are no longer able to take up any additional VFAs. So we can check the box for VFA generation and confirm it is in excess in the fermentation layer, but lacking in the majority of the reactor. Next step is to examine if we can transport the excess VFAs in the fermentation layer up into the bulk liquid so they can be utilized by other PAOs. After the previous VFA data was collected in April, the unique Biomix DC intermittent pulses were added to the control logic, and the VFAs were again measured in the fermentation layer. As Dave discussed earlier, an excess of VFA building up in the bottom tank is not optimal, as they can't be fully utilized by all of the PAOs. To maximize the use of VFA by the PAOs that can be found throughout the entire tank, we want to transport those VFAs up into the bulk liquid. But the key is we want to do that without disrupting the fermentation layer. The intermittent pulses of mixing during the deep cycle do just that. On this graph, you can see the blue lines which represent the time when each mixing pulse occurs. Next, we lay in the VFA measurements in the fermentation layer just prior to an intermittent mixing pulse. Finally, you can see the second VFA measurements after a mixing pulse. The drop in VFA immediately after a pulse demonstrates how the VFAs are transported out of the fermentation layer and into the bulk liquid, where they can be better utilized by the PAOs found throughout the tank. We also wanted to confirm that when we were transferring the VFAs from the fermentation layer into the bulk liquid, that we were not disrupting the fermentation layer that had formed during the long deep cycle operation. Handheld TSS measurements before and after each intermittent pulse confirmed the higher concentration sludge blanket at the bottom was not disrupted. So that checks our box for VFA transport into the bulk liquid. In order to discuss the proliferation of PAOs identified in the sludge, we must first look at an overview of the plant again. Earlier, we focused on train 1 and 2 of the plant, which are referred to as the west side. The entire treatment facility consists of 2 separate sludge streams with 2 independent activated sludge systems. The west side is a plug flow design with 3 passes. The east side has an anaerobic zone up front, just like the west, but then it flows into a complete mixed reactor. The east and west sides of the plant have separate secondary clarifiers, and thus completely independent sludge streams. This makes it ideal for comparing PAO populations using DNA analysis. One DNA sample was collected from both the east and west sides of the treatment plant, each from the aerobic zones. Both samples were analyzed for PAO species, and the results are shown here as % relative abundance in the sample. The DNA sample from the west side of the plant showed over 12% PAO relative abundance, whereas the east side showed just about 4%. For both samples, the dominant organism present is Dichloromonas, which, based on our research, is an important PAO along with the more commonly recognized Acuminobacter and Tetrasphaera. Dichloromonas are often abundant in full-scale EBPR plants and may also be important for nitrogen removal, specifically denitrification. The DNA analysis were also examined by microbe detectives for correlation to other samples they have received. Their database includes nearly 700 samples from 19 different treatment plants throughout the United States. The different blue bars in the graph represent the individual quartiles of data from their database. From this, we can see that both the east and the west samples fall within the top 50% of the data points collected at this time. When we discussed the results with microbe detectives, they indicated that the west data point is an outlier since it sits above the 4th quartile, and that is considered a good outcome. They also indicated that there are some other outlier data points that may be in that range that just aren't shown by the way that the data is presented in this graph. So with this, we're able to check the fact that our unique biomix DC operation is resulting in a proliferation of PAOs. Finally, we get to the results that matter most to any treatment facility. How does this impact my effluent quality? On this slide, we are showing two trend lines. The top line in orange is showing the influent total phosphorus entering the anaerobic zone, including that from the primary clarifier effluent, the RAS, and the side stream processes. The bottom line in blue is showing the effluent orthophosphorus from the west side of the plant, meaning it is from both trains 1 and 2, despite the fact that Biomix DC was only operated in train 2. The table on the bottom provides the average influent concentrations for each parameter as it entered the anaerobic zone. The black dotted line on the graph illustrates the date which we started operation of Biomix DC. There are two main things I would like to point out regarding the performance. First, the removal efficiency. Based on the influent and effluent data that we have collected from the plant, the average removal efficiency before implementation of Biomix DC was only around 65%. Often, the plant found themselves needing to dose ferric chloride to precipitate phosphorus for days at a time to meet their 1 milligram per liter permit. After using Biomix DC in just one of the trains on the west side, the average removal efficiency quickly jumped up to an average 95%. And that's not all. Despite the continued fluctuations in the influent phosphorus shown on the orange trend, the effluent orthophosphorus remains consistently low. This checks our final box, consistently low effluent P. After we completed our testing in May, the plant has now turned on Biomix DC in train 1 on the west side of the plant. We are looking forward to continuing to monitor the effluent quality of the west side versus the east side until we are able to complete the controls upgrade to allow the plant to operate both the east side and the west side of the plants as Biomix DC. Now that we've reviewed all of the testing data from Warren and checked the boxes for the most important factors that contribute to EBPR, I would like to review how Biomix DC can benefit you. When people think of operational savings, usually their minds go straight to energy savings, and Biomix DC does just that. A net energy savings of 90% can be achieved through the combination of eliminating complete mixing for long periods of time and the use of our high-efficiency Biomix mixing system. While the energy savings are very impressive, it's not the only way that plants save money. There's also substantial savings for plants that need to supplement BioP with either carbon addition and or chemical dosing for precipitation, specifically for plants that have low influent BOD to P ratios or low influent VFAs. Reduction in chemical used for precipitation directly results in reduction of sludge volumes and subsequently reduction of sludge disposal costs. Biomix DC provides unparalleled flexibility to meet the needs of plants of any configuration or size. Biomix DC is compatible with any and all other Biomix systems that may be on site, whether that be in an anoxic, swing, or post-anoxic zone within the secondary treatment process, or really any location in the plant that requires mixing. The applications shown here illustrate many of the opportunities for Biomix in a wastewater facility. Biomix DC demonstrates flexibility and compatibility with regard to how it can be used in many different fermentation configurations. The first of which is inline fermentation, where the primary effluent and the RAS enter an anaerobic tank that is operated as a fermentation tank. This configuration is what we saw in our Warren example earlier. This option is perfect for retrofitting existing anaerobic zones or repurposing excess aerobic volume at plants that don't have any additional tanks or room for newly constructed tanks. Biomix DC is installed in the anaerobic tank in this configuration, and biomix is used in the anoxic tank, where it provides constant mixing. Another configuration that plants may elect to use is side stream RAS fermentation. In side stream RAS fermentation, an auxiliary tank is needed to feed a slipstream of return activated sludge for fermentation. The side stream reactor utilizes the return activated sludge as the substrate for hydrolysis and fermentation to produce VFAs, which are then fed to the mainstream anaerobic zones. The hydraulic retention time in a side stream RAS fermentation tank may be between 12 and 48 hours. In this example, Biomix DC is installed in the RAS fermentation tank, and any anaerobic tank and biomix is used in the anoxic tank as before. Another configuration that plants may elect to use is side stream mixed liquor fermentation. In side stream MLSS fermentation, again, an auxiliary tank is needed. This time, a slipstream of the mixed liquor in the anaerobic zone is sent to the MLSS fermentation tank. This is often used when the plant's existing anaerobic zones need more volume to generate VFAs. Some say that side stream MLS ferments a higher fraction of soluble organics. For Biomix DC, it doesn't matter which of these configurations the plant determines is best for their process. Biomix DC works in all configurations and performs better than the traditional approach of just suspending mixing for long periods of time. Why? Because, as we have shown, Biomix DC checks all of the boxes needed to strengthen EBPR, including the very important objective of transporting excess VFAs to PAOs that are waiting to take them up. In summary, Biomix DC ensures an anaerobic zone with low ORP is present, creates a fermentation layer at the bottom of the tank during the long, deep cycle, generates VFAs in the fermentation layer, transports those VFAs to the PAOs that are present throughout the bulk liquid, resulting in a proliferation of PAOs in the mixed liquor, and ultimately consistent low effluent phosphorus. Thank you all so much for your participation and interest in our presentation today. Both Dave and my contact information is shown on the screen if you would like to contact us directly with further questions.